Okay.
Okay. Got it. Okay, so this is the second part of this lecture on radiocarbon, and of course, as I am a radiocarbon person working in archaeology and in the excavation, I talk a lot about our research in radiocarbon and how we develop new methods and new materials and new application also for this. So last time it was a short introduction about radiocarbon, and today will be on the new material, new methodology, and also on challenges for radiocarbon. In particular, I will give you an example when radiocarbon is indeed applied in historical period, when we have text and historical dates. Last time I introduced the new direction in radiocarbon research, in particular for the method, which is having the single year calibration, as you see here now. There is a lot of work going on in dating single year and not a group of 10 tree rings. So to make the calibration curve even more precise, more articulated through the 50,000 years that we have available for C14. And I think last time I spoke about so the new calibration, a little bit about new approaches with the infrared that we use very often in the field. And today we will speak a little bit more about methodology and new materials and some case study. I think we will mostly talk about this historical period. The dating assemblage, this concept that I have introduced last time, is very similar to what you can say, the assemblage, a pottery assemblage that we use in archaeology. But for radiocarbon, we have, especially for, in this case, for charred remains, I define this assemblage. I mean, this is a small patch of white material with charcoal. If you have all these characteristics, like you have your charred remains, ash, heated clay, phosphate, phytoliths, then you can say is in situ, and therefore is good for dating. And here we use the microarchaeology to define all these parameters and proxy for the in situ context, which is suitable for dating. Because we are not, we don't want to be limited only to the case that you found this beautiful context, which is very often very rare. So we do want to have other possibility in order to enlarge your number of samples that you can recover and you can date and build your chronology. So if we see here, charred remains is known to everybody as excavated because it is a small black material. It can be a seed, it can be a piece, a chunk of charcoal, but this is normally identified and put aside for radiocarbon. But there are other materials that could be used for that. For example, bones also. Bones, if they're found in a pit, in a refuse pit, in articulation, in a grave, then they're also good material for radiocarbon dating and to build the chronology. But there are others, for example, ash. Also ash, if it is in situ, like for example, in this case, you have ash with charred remains. Ash. Why ash cannot be dated or could be dated? I mean, this is another, this could be a material, ash comes from tree were in equilibrium with the atmosphere and with the C14 in the atmosphere. And so why not? Why we couldn't date ash? So this is about what we're going to talk now, new materials and methods that we have developed for radiocarbon dating, ash dating. We have made some studies about the possibility to use ash for dating, because every time you burn a tree, you obtain ash. So the ash comes from the tree, and we will see how. And so it could be a potential good material for dating. And then in this direction, we have found that, you know, in the ash, we should use the Aragonite for dating. And now we will see why and what is the story here. So ash, where does it come from? Ash. Ash is what remains after you make a fire. And it's not that we have ash inside the tree, of course, because ash is calcite, is calcium carbonate. There is no calcite inside the tree. Inside the tree, we have the calcium oxalate, calcium, carbon, oxygen, oxygen. And here we see this calcium oxalate crystal, this white one, which are inside, mark, for example, a ring in this tree. So this calcium oxalate, when they are heated during a fire, 450 degrees, they lose a carbon monoxide. If you lose a carbon monoxide, then you are left with a calcium carbonate. If you do your stoichiometric here, you know, then you lose one carbon and you're left with one carbon, and you lose one oxygen, so you are left with 3 oxygen here and your calcium. So you get the calcium carbonate. And this carbon here, okay, is the carbon that you have inside your oxalate, which should be the carbon that comes from photosynthesis, from the CO2. When the tree grows the ring, then you use the carbon that you obtain from the photosynthesis. So in principle, this should be a perfect one, because you should have the carbon 14 from the time it was burnt. Here you have the ash, the calcium carbonate, pseudomorph, which are still with the morphology of an oxalate, but from a point of view of material is already calcium carbonate. So it could be a good, but in this first study, when we did this first study with the assumption, you know, that ash should be a perfect material for dating, in this process of emission of carbon monoxide, this process is not in equilibrium with the atmosphere, so carbon monoxide can be introduced and exchanged, and this carbon monoxide is not as the carbon dioxide with the C14 used for photosynthesis, is not in equilibrium for as much as is the C14 is involved. So in this case, ash should not represent, is a very complicated material to date. But you see, if this calcium carbonate for some reason is heated at higher temperature, more than 600 degrees, 700, 800, 900 degrees, then a carbon dioxide is emitted. We are left with calcium oxide, and then with the humidity, some water, we have a carbon hydroxide, calcium hydroxide, sorry, and carbon dioxide is included in while the calcium hydroxide absorb the carbon dioxide, the water disappears, and we go back to calcium carbonate. This process, the second part of the process, is very similar to what is the process to make a plaster or cement, mortar, which is a material found often in archaeology. So in this case, the calcium dioxide here, which is included now in our calcium carbonate, should be a good material for dating. And it forms both calcite and aragonite. So because it comes from the atmosphere, it should represent the moment of formation of these two minerals. The difference between these two minerals, both are calcium carbonate, but they are different in their crystalline structure. Very small difference is in the disposition of the atoms. And aragonite is less stable than the calcite. So normally it's very difficult to find in archaeology aragonite, but if it is found, then unless it is a shell or biogenic aragonite, then it means that the carbonate material should be well preserved in the site. So, and if it is preserved, then it's most probable the original aragonite form in this moment. So it should preserve the C14 signature at the formation. And so if we could date this aragonite, then it would be perfect for radiocarbon dating and for chronology. For example, where can you find this aragonite? This is a long story, but one case it could be a destruction layer, a destruction layer which reach high temperature, and then it can get the ash can go through this second step in the burning. Then we can have a layer here. You see this. This is a destruction layer in Megiddo. There you may be able to find aragonite. And when you analyze this, you see this is our aragonite layers. It's a thick layer in this case. You can use XRD and you identify aragonite, calcite, and the other minerals. You can use the stable isotopes to identify the aragonite. You can use FTIR, the Fourier transform infrared spectroscopy, which is a method that we use in the field to identify the different minerals in the layers and in a way also the percentage. And the other proxy like phytolith, you can use microscope to check the composition, not only mineral composition, but also what else is in this layer. So this was our aragonite layer, and we thought that here, you see, we could indeed apply, this is our layer, we could apply our method, at least test the possibility and verify if aragonite is indeed pristine and we can date. Now, how do you extract the aragonite? Because in this layer, you have, together with aragonite, other material. You have the calcite, and the calcite, by definition, has carbon, but it's not by definition produced during the fire event. It could be also geogenic calcite coming from chalk, from limestone. Is calcite you have a present always in the sediment. So we would like not to have this calcite and have only the aragonite. So we needed to separate. Here we can use, you know, for example, you can separate by density because the calcite has a different density than aragonite. So this is one possibility, and you can indeed separate with the specific solution the two minerals. Verify that, for example, with infrared that you don't have any more calcite, and if you have only aragonite, then date with C14. Of course, this was like a new method on a new material, so we had to, you know, we need a known age ash layer, known age by other methods independent from the aragonite in order to prove that this methodology is correct. Now, by density, indeed, you can separate most of the calcite, but you have to keep in mind that this aragonite that is formed at a destruction event in this case, but through time it can include and can be contaminated by some calcite. So the density, this density 2.93, and the difference from 2.71 sometimes is a little bit, not precise. So then the separation might be not perfect. And if you would date, as you see here with the infrared, if you would date a material which still has some calcite, like you have it here in this shoulder that is shown here, then you may have a wrong date. So you really need to be sure that this calcite is gone and you have only the aragonite. Then you can use the difference in thermal decomposition between the two materials. If you take a calcite and you heat it, you will see that the decomposition to calcium oxide happen. Here is the peak at 753. Okay, so but it started a little bit, not before 600. You started to decompose your calcite, while for the Megiddo ash, you see that you start before 600 to decompose. So you could, we thought that we could use this difference between the geogenic chalk, in this case of Megiddo, and the ash of Megiddo to separate, after you separate it by density, the material which is separated by density, then re-separate with thermal decomposition and get the aragonite only for dating. So this development took several tests and control material to verify that indeed we have this separation completed. So when this was done, and we, on one side, we dated the layer with seeds, short-lived material, and we had a range of PMC for the seeds present in the destruction layer, which gave a kind of range between 2,920 and 2,760 uncalibrated. So when we use our separation with the thermal decomposition, then we obtain indeed the correct age for our layer, correct compared to the seeds. And we had a confirmation that by separating at best the aragonite from the calcite, which aragonite produce in a fire event at high temperature, this is a good material for dating. So this is a kind of a further material, further samples that is available for chronology. Then we can think about the bone, the collagen, which is the fraction in the bone, the organic fraction that is used for dating. And normally, when you see a bone, and you can study for archaeology or anthropology for research, that doesn't mean that it has collagen preserved. You see the mineral part and you can recover a lot of information from it, but maybe the dating is not possible because the collagen is not there anymore. The collagen is easily used by the bacteria through time, and it degrades very easily, especially in a warm climate, humid and warm condition. So for example, in the southern Levant, collagen is preserved, I don't know, I would say about in 40% of the case, if not less. In Northern Europe, it's much easier to find collagen in bones. So it's a perfect context in articulation, a burial. It would be a perfect material for dating if, of course, collagen is preserved. And the collagen is part of the structure of the bone together with the carbonated apatite, which is the mineral one. The carbonated apatite also has carbon, which is built with the carbon that come from the food that the animal eats, and could also be a source of material for radiocarbon dating. But since it is a carbonated group, then it can interact with the environment, and water can bring a new carbonate and exchange with the carbonated in the bone, and then your pristine signal of C14 in your bone is contaminated. So it's not possible to distinguish who is the original carbon and who is not the original carbon. That's why in radiocarbon we use the collagen. Either is there or is not there. With the infrared, you can see if you have or you don't have collagen, because you can you dissolve your bone, and the insoluble fraction that you can recover is your collagen. If it's there, then the infrared will show you these three peaks of the amide 1, amide 2, and proline of the amino acid. So now we are going to, because we had a very complex history in recovering collagen from bones here in the southern Levant, we started to think about the possibility to use what we call it the soluble fraction. So normally what you do, you take your bone, you add acid to dissolve the mineral part, and you will have your insoluble and your soluble fraction. The acid insoluble fraction is the collagen, is the one that is used for C14. The acid soluble fraction is normally discarded, okay? Because together with that, you may have contaminants and other particles, so you discard this part. And if you have the insoluble, which is your collagen, then you can use it for C14. Okay, you can check the percentage of carbon, CN ratio, FTIR, amino acid analysis in order to certify that your collagen is indeed pure. What about if you don't have this insoluble fraction? So we know, all right, we thought, is there a solution? Can we do anything? Because this fraction we always have. I mean, if this has degraded, maybe it has degraded into the soluble fraction. So the degradation of collagen is indeed, you know, fragmenting our initial fiber of collagen in smaller and smaller and smaller fraction. But the collagen has a property that it could reassemble back if it is done in a control pH condition. And that's what we try to do. And so we did take our bones, we dissolve it, but instead of to throw away the soluble fraction, which is normally quite a lot, we put it in a dialysis bag and we change the pH in a control way, and we recover the collagen which has reassembled in our dialysis bag. So it doesn't mean that is a good collagen. So that's why before dating and before using for C14, we do check that indeed what is insoluble here is indeed collagen. So here we have an example between a bone that has very little collagen, but this is the insoluble collagen of the bone, and this was the soluble fraction that has reassembled as collagen. And we see that the infrared spectra show very nice agreement between the two. So we did take a few bonds for control, and among these 6 bonds, sorry. So we had 5 which were in the expected range, were very close to the absolute, to the correct date of the bonds, which we measured using the insoluble collagen. So it is promising, but it requires control on the final fraction that is recovered to figure out that is good collagen. From this first study, we did several other research on that, and sometimes it's just impossible to recover any collagen. So the collagen is not there, not even fragmented or in the soluble fraction. So, but we can very often recover the soluble fraction and reassemble the collagen. So this is something that may help in increase the type of samples and the number of samples that could be dated to build the chronology. So as a case study, last time I presented a case in Jerusalem with the Gihon Tower, which was moved from its place in the 17th, 16th century BC, based on relative chronology on pottery. We move it to the 9th century BC, so quite a large difference. And I introduced last time the black wheel made ware, which is a very characteristic pottery that appeared in the southern Levant, and is a way to synchronize with the North Levant archaeology. The IBA in the southern Levant, Intermediate Bronze Age, now is about 500 years old, longer, it's 500 years longer, and it covered the same period that in the northern Levant is the EB4A and EB4B. And this black wheel made ware is a very characteristic pottery, is black and has these white drawings, and it has been given a lot of social meaning in this, in understanding what is going on in the IBA in the southern Levant, because the IBA in the southern Levant is made of small sites. People are moving around. The society is more agriculture or herd related. So is from the urbanistic period, which ended 2500. Now we are moving more to an agricultural society. But this pottery is very specific, and being a connection between the north and the south, it was important to find this, to date with in absolute way this pottery. This was the PhD of Ron Lever at the Weizmann Institute. So during his PhD, it was aimed to build the chronology of the IBA, not only of the black wheel made ware. And we were lucky that excavating few sites like Hatzor, Kishron, Azorea, and Kfar Vradim, excavating these 4 sites, we found this type of this pottery. So, so we had the opportunity to excavate the context, figure out that the context is well preserved, is in situ, use the microarchaeology approach for chronology, and recover samples in situ related to this pottery. In comparison with the northern Levant, where 3 sites only had absolute C14 dates for these potteries, Vaduz, Khirbet el-Umbashi, and Tel Arka, we have that the C14 has very wide range for this pottery. Let's say that it could be also a little bit too extreme for this chronology, and other sites dated the presence of this pottery using relative chronology and stratigraphy. And you see that these cover the whole period. Now we know that the change here, EB4A to EB4B, is very much also related to the destruction of Ebla and to the change in pottery style, which is connected to the appearance also in the southern Levant of this black wheel-made ware. So the type of context that we were able to excavate, like this one in Kishron, was an in situ abandoned room with a lot of grape seeds inside the pottery. So we had a good data for at least in Kishron. These are the dates that we have collected and measured at the Weizmann. And you see that they are all, these are the different sites, Kfar Vradim, Kishron, Azorea, and 3 from Hatzor. They, in the calibrated range, they are between 2,200 and 2,400, but most of them are in these 100 years. So the different sites are very close in age and in the context where this pottery was found. So already, without any modeling, any Bayesian, just face value of the dates, we can say, you know, that the black wheel-made ware probably appeared in the southern Levant, certainly in the 23rd century, and possibly it started sometime, maybe in the 24th century, could be. This was the situation that we had in mind. So this is the 23rd century for, we are not, we are very well overlapping with what we have in the North Levant. Even if you do some modeling with this data, also there are not many, but you can think according to the stratigraphy and the context that we have excavated to build up like a terminus postquem, terminus antequem, trying to see if there is, if you can restrict the appearance of the time of appearance of this pottery, and it is altogether, you know, in the 23rd century. So the general picture that we have now between the North and the Southern Levant, with the black wheel-made ware peg, which is very, very unique, is that in the Southern Levant, here you have the unmodeled distribution of the dates. We we start very much closer to the beginning of the 23rd century. So exactly when there is this change between the EB4A and EB4B in the northern Levant. So the communication between north and south, if from the north this idea reached the south, so was very immediate. It was very, very fast. So if there will be more precise dates, more dates also for the North Levant, then we can start to have a better idea how this new pottery reached the southern Levant and guide the interpretation, the social interpretation of this high-level ceramic had in the rural society of the southern Levant. The other case study is in the historical period. Historical means from 0 onward in the AD range of C14. We are talking about Jerusalem at the Roman time, a period that we have text, we have records, we have inscription and absolute dates, and a period that not only in Jerusalem but in general is has not been studied using C14, because we have coins, we have, as I say, text, and so it seems that C14 accuracy and precision is not as good as the historical record. But and another problem is that we are not in a town, but we are inside a city in an urbanistic environment. So it's not like layers above the other, but it's more really a puzzle that built inside the different tessera of the puzzle. So quite complicated. So we are at the Wilson Arch in Jerusalem. So the Wilson Arch, here is the Temple Mount, here is the Western Wall, and the Wilson Arch is there. So we are really in a modern urbanistic environment, but also from a historical point of view and archaeological point of view, we are in an urbanistic environment. Today, when you look at the Western Wall, so the Wilson Arch is here. That's what you see of the Wilson Arch here. This is visible today, and of course it is much deeper inside. So it is related to the Robinson Arch, this one, which is completely disappeared almost completely. We are left only with the top part when you get to the wall. This is the other arch. And in the last century, in the beginning of the last century, this was the view. This is what we say the Robinson Arch. This is what we saw here. So there were sediment here covering all these sediments. Yeah, we have the people walking very close to the Robinson Arch remains. So all this has been excavated, and this is another view of the Wilson Arch that is not visible, but is down there. So a reconstruction of the temple at the time of Herod is represented here. So this would be the Robinson Arch, and this would be the Wilson Arch. And this structure is totally disappearing. And this was built by Herod in order to facilitate the entrance to the temple for the Jerusalem and for the visitors of the temple. So the Wilson's Arch. But it was a discussion among the archaeologists who actually built the Wilson Arch, and also who doubled the size of the Wilson's Arch, because of from its original size, the width of the arch has been enlarged. And what happened under the Wilson Arch after it was constructed? The discussion was that yes, indeed, it was Herod that built it and enlarged it, or only built the first part and the second part was built later by maybe the Roman or another emperor later on. And there was also a suggestion that it was built, it was enlarged during the Islamic period. This is how it looks. The Wilson Arch today is on the top. There is a synagogue to pray towards the Western Wall, and the excavation that started in the last few years was aimed to leave the synagogue on the top and on the bottom make available for the tourist to visit under the Wilson Arch. Here is the Western Wall, and pass through and visit the base of the under the old city of Jerusalem. So it was necessary then, this was the synagogue, to excavate in the last few years all this part. And that's how we came to, in our, with the grant that we had from the ISF, Israel Science Foundation, we came in. So the challenge for C14 was indeed quite complicated, because as you see, we have Herod, which is from the 30 to 4th AD. Then we have a sequence of other rulers in Jerusalem, which, as you see, you know, in 50 years, for example, we change 4 different rulers. Can C14 have a good input in this chronology and figure out exactly when the structure was built? Because we know also that the historical narration sometimes is false, and the information that reaches us needs to be in a way corrected. So at the best, even when C14, you see, is measured with plus minus 15, you still have in this period, this is the new calibration curve, you still have that all your interval is about 70, 100 years. Okay, so, you know, this was at the best, even, you know, in the best condition. Can we do better than this? So here you really need a strategy, and this is what we indeed built for that. In the moment they start to excavate, we follow the excavation every week in order to see the progress, to see the new strata that are appearing, excavate the context which seems the most suitable for the chronology, look for sample for reproducibility, because it's not enough to date one layer with only one samples. You really need to reproduce the same age for the same layer, if this is the hypothesis behind the chronology. That's how we start. This is the synagogue floor where the people are praying, and you see all these was filled up with all kind of sediments and construction material from 2000 years till the Ottoman period. So there is, of course, modern material, but it's important to start to figure out what is in situ and what is not in situ, because any good context which is detected in layers from the top going down as archaeology excavate is always not only represent the time for that layer, but is a terminus ante quem for all the layers below. So any excellent context should be sample and dated. And talking about a construction material, because sorry, the Wilson's Arch was constructed with limestone, and between the limestone there was a mortar that was set there at the time of the construction. So the material we had most available in this case was not a fireplace with ash and charcoal, was not a burial, was not a refuse pit or a pottery full of grains that burnt in situ. This was all construction material. And in this construction material, we had to look for good charred remains that could be used for C14. So the question was also if we were looking for construction or renovation, because it could be that in some cases there was a renovation, so the material was introduced later, so the date of the material would date the renovation and not the construction. Then pristine and uncontaminated, because very often in this type of excavation, when you uncover structures, they need also to be immediately preserved if they are ruined through time. And if the preservation people had modern material, then we needed to know that the material is not the original one, because often they used archaeological material to repair the archaeological remains. And so it's very hard sometimes to know if it is, the original one, or it is mixed, and the preservation people added this into the structure. Also, how many samples do we have to take in order to absolute date a structure? We know that one day is not date. You have 70 years. So if we want to build also a model and try to make the range of the calibrated age smaller, then we need as many samples as possible, but also see if the layer has is one moment or is has a long life with the radiocarbon. So it was really starting from the very beginning, and Dr. Joanna Regev was there every week to check the progress of the excavation and collecting, checking materials and samples for the chronology. Yeah, it's important that you have to reproduce the dates also to see that it's really you are really sampling the same moment in there. The material, once it is collected, we work in the lab for the characterization of this material. We will the material, as we say, is very often in this situation. The material that we want to date is indeed the charred remains, but it comes out from mortar and cement that was used in the building of the structure. So the preservation of the mortar, of the cement, needs to be studied to see if there are any transformation that could indicate to us inclusion of contamination, and that could also contaminate our charred remains in the mortar. And also, if we were collecting mortar from different location here, and we think this is the same event, we characterize this mortar with the infrared. And as you can see from the spectra, these are three different mortar from three different periods in the Wilson arch structure. And you see that, for example, here you have much higher clay than in this case. And here the clay is not burnt because we have still the peak of the water, of the structural water, while in this case it seems that the clay was indeed burnt. Maybe it was broken ceramic added, but the peak of the clay is 1037, and we don't have the structural water. So these are all methodology that we have built through time to understand better the archaeological material. And if, for example, if this reproduce for all the mortars in the same layer, in the same structure. So, and beside the characterization of the composition of the mortar, we also check if this mortar is still in a good state of preservation, if it is mortar like a mortar or plaster that has been done through pyrotechnology, or maybe there is a strong geogenic composition present inside the mortar. And this is done with what we call it the grinding curve, that use the height of these two peaks, which are related to the calcium carbonate, and the width of the major peak for the calcium carbonate. So the grinding curve, when you use the height and the width of this peak, so it tells you if your material is in the crystalline order of the calcium carbonate, closer to the geogenic material, or closer to the like plaster material. Okay, so anything in between is a different type of crystalline order, which is an indication of diagenesis, but also of how the material was indeed made. And so the different mortar has been both analyzed with the infrared and also with the grinding curve. So here we have these are the standards that we use for the characterization, and the points are the archaeological material. So as you see, the Byzantine, for example, the Byzantine material, this one, as a composition, it seems very much that they just mixed the chalk, the limestone, unburnt with in some plaster, and so it's very different from the other material in the structure. So a lot of this has been done in all these Wilson Arch, from as it was uncovered, and not only on the Wilson, of course, in all the different walls we will see that were uncovered there. really to map the structure, map the construction material, and also when we do the dating, to add this further information of reproducibility of the building material into the radiocarbon data. And by looking at that, we were able even to find some straw still preserved in the mortar, and extract the straw, which is very small. I mean, these are 5 millimeter, and you see that this straw is very small, and we had to collect a lot because still we wanted to check that this straw is still a cellulose, as it should be initially, and indeed by checking that this is still a cellulose, then we felt confident that dating this straw would date the construction of this structure. So once we have all this material, of course, at the accelerator, the determination of C14, which is done on the graphite obtained from the sample after it has been cleaned and graphitized. The measurement is done with many known age samples in order to improve the precision of the measurement, and also, when possible, repeat the measurement of the same samples more than once. So really to gain in precision in order to reduce as much as possible the calibrated range of the samples. So these 9 meters, these are 9 meters of excavation that were done during 3 years under the Wilson Arch. Here you see in scale, this is the side of the western wall. So there were some layers that were coming down, and then here is already the theater. So we will focus because we go from the modern material in these 9 meters. We pass through the late Islamic, Byzantine, Roman, and we were mostly interested in this part. But we dated also, when possible, we dated also the top part of the sequence. So going down here, we start to see this huge deposit, very in layers. So here we are in the Byzantine period, and then as we start to go down more and more and more, here you have the image, we start to uncover the shops or the rooms which were built under the Wilson Arch. So these sediments, you see, they fill up the room, at least up to a certain point. So at the end here, when all the 9 meters were excavated, here we have the rooms or shops that were under the Wilson Arch, facing the western wall, and we have here, as you see, a small theater, a small Odeon. So was it this? So here is the other view when the Odeon start to be uncovered here. You see. So the situation was quite complex. It's not a tail. It's not layers one on the top of the other, because this theater was built under the huge arch, and was probably built later, after, not at the same time with the arch. The pottery was Roman, but could not give better resolution than 250, 480. So it's this is because the place was used also as a dump very often. So it could have been a material that came from removed from other locations. So it was not the pottery was not really helpful in this case. So this is the theater, the shops, and we try to recover samples from all these structure, from the shops, from the seats of the Odeon here, which was, as you see, they were all removed and destroyed. So we had to look very, very carefully in order to find in situ location inside the seats of the theater. There was this yellow material, opus cementitio, which is a structure that appears in different parts of Jerusalem. And also here, it is like the earliest material present in this location. So this would be the terminus postquem for all the structure here. Okay, so this is when you face from the western wall, you face the other side of the arch. Then you have the rooms, and it was clear that there was here was the addition of here was the enlargement of the arch. So this was the original one, the first one, this part, and then it was double the size later on, maybe from 20 BC, like was it immediately they recognized it was too small, the arch, and they had to make it larger, or was it up to 700 AD when the Islam, during the early Islamic period. So these are all the different rooms that has been investigated, and the location under the room in this yellow material here at the top of the inside the room. So any possible context was sampled and was checked. Here we have, for example, the height of the deposit inside the room. So this part was not covered by any deposit, at least from the time it was built. So that was an excellent opportunity to sample this context or this context. Also here we see the line of the deposit. And these are most of the location, and in the paper in +1 that we publish, there are all the details for the characterization of all the different mortars in the different rooms, which gave us confidence that the structure and what we have sampled in practice was one event. So here more details about the condition of the context, which if this is the Byzantine, all this was covered with the Byzantine damp, then mortar down here would have been easily contaminated by that. So that's why this part of the room, the top part, have been preferred in order to date the structure. More details. So we really work very close to the excavation when this was, as it was available for sampling. So we try to map with a C14 all the rooms and the base of the Wilson Arch on this side, and the theater too. The theater was a very interesting structure because we see that between the northern part and the southern part, the pedestal was not completely finished. The southern part had all the finishing already done, while the northern part was not yet finished. It should have been symmetric and be the same, but it was not. And the same appear also in again here. The stairs in the northern part, it was not finished. The steps to go up to the sitting seats, while the southern part was finished. What happened here? I mean, why this nice Odeon was not finished? So it was very very interesting because it's a small structure by itself, and it was under the Wilson Arch, so it could have been close to the second century AD. So the Wilson Arch is earlier than this theater structure. Well, it was most probably an Odeon, so for a small exhibition or I don't know, politics. I don't know. But the building was not completely. This was very, very surprising. And it was sealed during the middle of the 3rd century. It was covered by a dump. So in this time frame, the candidate that could have helped or could have, seen the construction, was it maybe Adriano, that because he refurbished Jerusalem and he founding this Ilia Capitolina in the 130 CE. Was this the major push to build this theater, small Odeon under the Wilson Arch? And then the Bar Kokhba came in and started Bar Kokhba revolt, stop the construction, and then Adrian death in 138, or was it? So it was an interesting question, and we try to answer with the dating. And here you have all the 32 dates that were measured from the latest one that we could date in the end of the 14th century here. Then we have a gap here of dates between 700 and 1200. And this is the part here that we were mostly interested about the Wilson Arch. So we start from the yellow mortar, this yellow material, which is before the Wilson Arch. And then we have the northern pier, which is the first one to be built. We have a channel. And then we have the southern pier, which is the second one to be built, the widened. And then we have the theater phase. So these are the dates, and you can we try to model them according just as a sequence of how the structures were built. And you see, when you do the modeling, you see that the black part, the darker part here is what the model suggests should be the correct date of that sample. And the light gray part is the actual date. So in some case, most of the case, the black part is included, is covering part of the light gray date. And you have here the agreement between the model date and let's say your date. So when it is more than 60 is okay. For example, in this case is 60, and you see that the model would say, well, your data should be here, but actually you measured here, and probably there is a little part over there. So it's not the optimal, but is not impossible. But most of the dates are in a perfect agreement with the model and the data we obtain. And interesting is that the first part of the northern pier and the drainage channel were built, most probable, by King Harold the Great, while the southern pier, the dates of the southern pier are between 30 and 50, 60 CE. So apparently this part of the Wilson Arch was constructed under the Roman procurators period. The theater, so as you see, the theater seems to most probably started before or immediately when Adriano announced or founded the Ilia Capitolina, and it was not finished. Apparently, is synchronous with the revolt of Bar Kokhba. So if this was the reason, the revolt, to stop any further development in Jerusalem, seems sustained by this date and model, and until and so it looks very very well founded. So as you see, radiocarbon chronology in this case scope against the historical dates. We can certainly say that the southern pier was not built in 700. This is easy, but was not built also by Harold. So the southern pier was built later after the death of Harold the Great. I think that working in the message for building a chronology with C14 is certainly not only to have a lot of samples, but context, field work, is for us is super important and is the first step to build the chronology, because you figure out the stratigraphy, but also how many samples you needed to take, reproducibility of the same date, of the dates for the same layers, trying to find the best context and material in the field by also adding all this microarchaeology that help to increase the number of contexts that can be dated. In the laboratory, it's not just an applying recipe, but each samples as is history and is nature and state of preservation. And so attention to how they behave, the samples, is necessary in order to assure the accuracy of the data, because 1 milligram of carbon is easy to find for the dating, but if this carbon is not from the original material and that has been tested for that, then the number, the data has no meaning. Also the accelerator, which seems, the standard procedure, and is not at all, because according to the chronological question, the number of background or standards or known age samples needed to be prepared and tailored according to the chronological question. If we are in an historical period, then we need many more known age samples for to reduce to make the precision better, reduce the error. If you are in 40,000 years old period, then you need more background to figure out that you know, the material is uncontaminated, and also your procedure is very clean. So it depends. It's not a standard, and so you can't measure the short, young samples with very old samples and obtain the same precision. So that's the research with radiocarbon is starting the field. It is in the lab, and then in the accelerator, and then you know, you can go to the calibration curve, and once you know with initial samples if you are in this period or in a plateau, then you know, you have a better idea how many samples you have to measure, or more stratigraphy to be studied, and then you can model your chronology. So all these should be followed through all the different steps in order to build a high precision chronology, and working with the radiocarbon expert, that's essential in order to get a better accurate and precise chronology. And I think that yeah, I finished. Thank you very much.